Inside every machine that prints an advanced computer chip, this is happening 50,000 times a second. A generator drops molten tin, one droplet at a time, each about 25 microns across, roughly a quarter the width of a human hair. The droplet falls through a vacuum at around 70 meters per second. A laser hits it twice. The first pulse flattens it into a pancake. The second vaporizes it into a plasma at roughly 200,000 degrees, which is well over 30 times hotter than the surface of the sun. In that instant, the dying tin gives off a flash of light at 13.5 nanometers. Extreme ultraviolet, the only wavelength short enough to carve the features on a leading-edge chip. Then it does it again, 50,000 times per second, for months, without missing. One company on Earth has made that work reliably. It took about 30 years and tens of billions of dollars, and when national labs started on it in the 1980s, plenty of serious physicists thought it was impossible. Here's the number that explains why anyone would want to replace it. That source puts out a few hundred watts. An EUV light is absorbed by almost everything, including glass and air, so it can't be focused with lenses. The whole optical path is mirrors. Even the best mirror humanity can manufacture loses roughly 30% of the light every time the beam bounces, and the beam bounces around 11 times before it reaches the wafer. Do that arithmetic, and only a sliver of what you started with survives. So there's a race to build a fundamentally different EUV source. 3 teams, 3 approaches, on 2 continents. And the thing almost every version of this story gets wrong is who is on which side. Start with why ASML has no competition. The company doesn't build the whole machine alone. The lasers come from Trumpf in Germany, the mirrors from Zeiss, and the plasma source traces back to a California company called Cymer that ASML bought outright in 2012. What ASML owns is the ability to make all of it work together, tens of thousands of times a second, for thousands of hours without failing. A standard EUV machine runs upward of $200 million. The newest high-NA generation is around $380 million, and SK Hynix placed a single order worth $8 billion this year. There's also a hidden cost. Firing 50,000 tin explosions a second inside a sealed chamber is a filthy business. Tin vapor coats everything, the chamber has to be flushed with hydrogen, and the collector mirror degrades anyway. Every hour spent servicing the source is an hour a machine worth hundreds of millions isn't printing anything, which is what the alternatives are attacking. Now the physics. Forget tin droplets. Picture a racetrack for electrons, a storage ring, the kind you'd find at a national physics lab. You accelerate electrons to nearly light speed and send them looping. Normally those electrons travel in loose clumps about a centimeter long, and they radiate like a messy light bulb, nowhere near intense enough to print chips. The trick is to squeeze them. Using a carefully tuned laser inside a device called an undulator, you nudge the electrons so that after a full trip around the ring, they snap into extremely tight, evenly spaced microbunches, each around a micrometer long. Packed that tightly and that regularly, their light waves line up. They stop radiating like a bulb and start radiating like a laser, and because they keep circling, they keep doing it continuously. That's the whole idea, and it has a name: steady-state microbunching. The contrast is the point. The tin approach is a strobe light, 50,000 violent little explosions a second with all the debris that comes with them. The ring explodes nothing, just a smooth, continuous river of light. One more thing about a ring, and this is the part that changes the economics. Because the electrons circle a big loop, you can place many lithography stations around the outside and feed all of them from the same source. Build the expensive part once, hang the tools off it. Now, where this idea came from, because the coverage gets tribal here. It wasn't invented in China. Steady-state microbunching was proposed in 2010 by Alexander Chow, one of the most respected accelerator physicists alive, working at Stanford with his graduate student Daniel Ratner. Then it sat on paper, because nobody had a machine suitable for testing it. A young physicist named Shuji Deng, doing his doctorate at Tsinghua University, pushed the mathematics much further, and Chow personally connected the Tsinghua group with accelerator physicists in Germany. And here's the detail most coverage skips entirely. The experiment that proved it works didn't happen in China. It happened in Berlin, on a German storage ring called the Metrology Light Source, with the German National Metrology Institute and the Helmholtz Center. The results were published in Nature in February 2021. If you want more of these, the ones where the story turns out to be structured differently than everyone assumes, subscribe and turn notifications on. Because now the part that actually reframes this. In Palo Alto, a startup called X-Light is chasing the same physics from the other direction using a free electron laser. In June 2026, a startup called X-Light, need not duplicate or alter. Let's carefully produce. In June 2026, the U.S. Department of Commerce finalized a $150 million award to the company under the CHIPS Act, taking an equity stake. Its executive chairman is Pat Gelsinger, the former chief executive of Intel. X-Light claims 4 times the power of current sources and says a single system could feed more than 20 scanners. Read that again. Feed 20 scanners. Whose scanners? ASML's. X-Light isn't building a rival machine, it's building a light source to plug into the machines ASML already sells. ASML has lent it basic support and has reportedly been in talks to participate in X-Light's next funding round, alongside TSMC, Intel, and Micron. The company supposedly being disrupted is helping fund the disruption, which tells you the premise was wrong. The light source was never the moat. Now the honest part, and there are 3 things here. First, ASML's monopoly is the scanner, not the lamp. The optics, the stage precision, the overlay accuracy, measured in fractions of a nanometer, and 30 years of learning how to make millions of chips where almost none come out defective. That last part is what money cannot shortcut. A better light source shining into a worse scanner prints nothing. Second, the Chinese effort is far earlier than the headlines suggest. The 2021 Berlin experiment demonstrated a mechanism using a tiny fraction of the charge a production source would need, and the most recent published design work from the Tsinghua Group targets kilowatt-level power at 100 nanometers, with 13.5 described as the more ambitious goal beyond that. That's a real gap, not a rounding error. Third, the incumbent is not standing still. ASML announced progress on a 1,000-watt plasma source in February 2026, and argues that past that point, other things become the bottleneck anyway, like how fast the stage can move and how sensitive the resist is. So here's where this lands. There genuinely is a second road to the most important light in the world, and it runs through a particle accelerator instead of a tin explosion. That road was mapped at Stanford, paved in Berlin, and is now being built in 2 countries at once. But it doesn't lead around ASML. For America, it leads into ASML's machines. For China, it only matters if they also build the scanner, the mirrors, the resist and the metrology, and the light source is one component out of roughly 100,000. The monopoly was never the hard part of the light. It was everything the light has to pass through afterwards.